This section we're going to define electromotive force and do examples of electromotive force, EMF, and try to understand what's going on there. So EMF, the definition. This is given by the energy or the work done per unit charge, so it's in volts, by non-electrical forces, for example the chemicals in a battery, which make the charge move around the circuit. Another way of looking at it is that the total energy difference per unit charge around the circuit, in other words the total energy per unit charge made available by the chemical reaction in the battery, or the total power per unit current used around the circuit. This is sometimes given power per unit current. Okay, so we need to try to explain and look at really what is this EMF, what is it, what is the difference between the EMF and basically the voltage given by the battery, because they're not always the same. And we're going to have to look at this now. So we have the most basic circuit here. This is a short circuit. It's a 6-volt circuit, and the battery or the cell we've put inside this little box here. The battery itself, or the cell, has some internal resistance, and we've labeled this one here as well. And then there's what's called the load, which is what's outside the cell. So what we have here is that we have two resistances. There's a resistance inside the battery, which is R. There's a resistance outside the battery, which is R. Now this voltage, this battery is able to supply 6 volts. However, some of the voltage will be lost, some of the potential difference will be lost inside the battery, some will be lost outside the battery. These resistances are the same, so basically half the voltage will be lost inside and half the voltage will be lost outside. So this, when you apply a voltmeter across the load, across the external resistor, you're only going to be able to measure 3 volts. In other words, this battery is only able to supply 3 volts because 3 volts is lost inside because of the resistance in circuit. The EMF is the 6 volts. This is what is able to be, this is the energy per unit charge to go completely around the circuit, including the internal resistance. But normally we don't see that. You're not able to see this full EMF, the full 6 volts, because some is lost inside. What happens if we change the external resistor? Here we have the same circuit again. And this is identical as before, but let's say we have a much larger resistor. This resistor is, let's say, 5 times as much as this one. So the total resistance here is going to be, let's say, 6 units of resistance, and we have 6 volts. This is 1 unit of resistance, this is 5 units of resistance. So effectively what we have is that 1/6 of the resistance is here, 5/6 of the resistance is here. So the voltage drop across here, the potential drop across here will only be 1 volt, and there will be 5 volts across here. So basically, as the load gets larger, voltage that we're able to measure, the potential difference we're able to measure across the cell, gets closer and closer to the EMF, which is the ideal voltage which is supplied by the cell. So with a small load, like this one here, with a large current, the internal resistance takes a bigger share of the EMF. In other words, here it takes 3 volts out of complete potential difference of 6 volts. Here it only takes 1 volt because it's a much smaller resistor compared to that of the load. When calculating the EMF, you have to consider the potential drop across the components in the circuit, in other words the load, and what happens inside the cell, or in other words the potential drop across the internal resistor. Now a battery has a very small internal resistance, but if the current is large, the larger the current, the more significant the potential difference drop across the internal resistance will be. So this is why we must have a large external load. This is the potential difference drop across the internal resistor. This is R for the small I is given for the internal resistor, and I is the current that's going through. So we want to basically measure the largest voltage that we can get. When is this going to be when is this voltage going to be 0? When is the potential difference drop across the internal resistance going to be 0? When is this value going to be 0? In other words, all the potential differences on the outside. Well, this is when the current will be 0, strangely enough. So when you measure across a battery, the voltage across the battery, you are going to measure the EMF if the current is 0, because it means that there's no potential drop across the internal resistor. Here we have another circuit. This is the load, this is the internal resistance, this is the cell. So this V is what you're able to measure by the load here. There's also a drop in the potential inside the cell, which is IR, this I small r. Inside the battery there's a certain amount of resistance, and this is called the internal resistance. We have a series circuit with two resistors, capital R and small r. We know that these voltages, these potential differences, will add up. So we know that the EMF, which is able to be supplied by the cell, some of it will be used up on the external circuit, which is capital V, which is what we measure here, and some of it will be IR, which is the internal potential drop, the internal voltage. So the actual potential difference provided by the cell will be this capital V. This is what we're able to measure. So we rearrange this. So what we measure by applying a voltmeter across the load is equal to the EMF minus the potential that is lost, the potential difference that is lost inside the battery. When the current is 0, then this term is 0. What we measure is the EMF. So what happens when I is equal to 0? Well, we're able to measure the EMF then. As soon as there is a current, some of the potential difference is lost across the internal resistance of the cell. In this case, the current is 0, so when we measure the EMF here, it will be equal to the, when we measure the voltage here, it will be equal to the EMF. Here we have an example. Here we have the EMF is 12 volts here. This internal resistance is 2 ohms, the external resistance is 22 ohms. So it's a large external resistance. So we're going to be measuring something close to the EMF. What will be the potential difference supplied by the battery? Well, it's not going to be 12 volts because some of this potential difference is lost inside the battery. The total resistance is equal to 22 plus 2 is 24 ohms. So we use V is equal to IR to find the current. I is the current, is V, which is the 12 volts, the EMF, divided by 24, which is the resistance, the total resistance. This gives the total current in the circuit, which is 0.5 amps. Now the potential difference across R is equal to V is equal to IR. 0.5 times 22 is equal to 11 volts. So in other words, this is able to measure the potential difference across this is 11 volts. We know this supplies 12 volts. There must be 1 volt lost inside the cell. What if the resistance were changed to 10 ohms instead? So this is a 10 ohm resistor. Well, let's find the total resistance again. It's going to be 12 ohms this time because this is 2 plus 10 ohms. So the next one is to find the current using V is equal to IR. I is equal to V over R. V is still 12 because that's the EMF supplied by the battery divided by 12, which is the total resistance. So now we have a larger current, twice as much current, so it's a 1 amp current. So what about across R? Well, we find V is equal to IR, and we find the potential difference across the external circuit, the load, is now 10 volts because the current is larger, which means we have 10 volt drop across here. This supplies 12 volts, so there must be a 2 volt drop inside the battery.